Okay, so today we're very happy to have Hirosi Ooguri from Caltech to tell us about symmetry-resolved physical states. Hirosi, can take it away.
Okay, all right. Thank you. Oh, something happened.
I'll click it forward.
Oh, I guess you need to do that.
Yeah, I can do it.
Right. Okay. Thank you for giving me the opportunity to talk about some of the things I'm thinking about. So I would like to explain the title. So, so I'm interested in thermal behavior of conformal field theory. There was somebody talking about conformal field theory earlier, and so we all know this is undergraduate stuff that if you calculate partition function. So I'm interested in unitary conformal field theory in these space-time dimensions. When I write D here, means space and time dimensions. So. So if you calculate, say, partition function trace of e to the minus beta h here, then by simple dimensional analysis, the leading term should be proportional to t to the d minus 1 with some positive coefficient. So this follows simply from the following consideration that, well, we know that this is an extensive term, that this should be like, in thermodynamic limit, this should be free energy divided by temperature. And free energy is extensive, so it should be proportional to the volume. And the only thing that is conformal field theory, so you should have t to the d. And so that's the sort of way that we can see it's extensive. And then, well, to be precise, well, so say it backwards. So this should be proportional to volume. So that means that, but you have to turn the volume into something dimensionless. So that's why you have to multiply t to the d minus 1. Okay, so that's good. And so in particular, for example, in 2D conformal field theory, this coefficient is given by the central charge of the Virasoro algebra. So that's the celebrated Kaji formula. So that everybody knows. And but when the conformal field theory has some symmetries, then it's useful to divide the Hilbert space into the representation of that symmetry. And then it's an interesting question how Hilbert space gets decomposed into that. And so that's what we teach undergraduate students, that it's useful to divide the Hilbert space into representation. So that means that we can also consider dividing this into representation and how it behaves for large temperature. So this sounds like a very basic question. Interestingly, nobody answered that question, so I'll answer that question today. And then it's also interesting in the context of ADS-CFT correspondence, because when you have a gravity dual of these kind of conformal field theory, and if the conformal field theory has some global symmetry, then that means that in the gravity side, you have to have a corresponding gauge symmetry. The gravity side over here cannot have global symmetry, and this has been long conjectured by many people, and this was recently proven by me and Daniel Haro. So as an introduction to this talk, let me first review this proof. So in order to prove that gravity theory has no global symmetry, so the gravity theory have gauge symmetry, which correspond to global symmetry of the conformal field theory. And in order to prove that gravity theory cannot have gauge symmetry, we use what's called entanglement with reconstruction. So this is a refined version of ADS-CFT. ADS-CFT says that if you have a gravitational theory inside of ADS, then there is a dual conformal field theory, and everything that is happening in gravity side over here can be described in terms of Hilbert space of the conformal field theory. Also, for example, if there is a local excitation over here, this cursor is a little bit pointed, a little bit delayed because I'm using Zoom. But I'm doing this because the people watching over Zoom can see the point. So please bear with me. And so for example, there's a local excitation over this bag. Then you can actually encode that information on the boundary conformal field theory. But as people studied detail about ADS-CFT correspondence, and here is Ahmed, for example, they realize that there is a more refined version of correspondence, which is to say that suppose we have some kind of excitation over this gray point over here, then you can encode that information about information about this excitation. You can encode it in the entire Hilbert space around the boundary, but you can use smaller Hilbert space, which is just consider this region B and C over boundary, and then consider a subspace of the Hilbert space corresponding to the excitation in B and C. And that's already know about this excitation C. So the question of how you decide which excitation got encoded in which part of the Hilbert space is the following. So suppose you pick some region like this. So let me draw. Oh, I cannot draw it here because people won't be able to see it, but doesn't prevent me from doing that. So suppose I have this boundary over here, and then suppose you choose some region over here. So then what you do is that you choose what's called Ryu-Takayanagi surface, which is a minimum surface that's ending on the boundary of this region. It's called Ryu-Takayanagi surface associated to this region A. And then consider this red shaded region between Ryu-Takayanagi surface and the boundary A. And anything that is happening locally as a sort of gravity excitation over here can be encoded in the information over A. So that's called entanglement wedge reconstruction. So this region is called the entanglement wedge, and anything that can be happening over here can be encoded in this region A. Okay. So that's what this is. But then this raised some question. This raised an interesting question. So that was raised in this paper and was answered, and which is the following. So suppose again I consider this gray point over here. Then you can consider B and C, union of B and C, and then there is a Ryu-Takayanagi surface over here, and then you have this red region. And then you can, this means that you can encode this information about this gray dot in the union of B and C. But you can also do that for A and B, and you can also do that for C and A. So you have the same information can be encoded in 3 different Hilbert spaces. Okay? And there is also the surprising situation, so a puzzling situation, where you suppose you consider complement. So suppose instead you consider A here. Well, the fact that you can encode information about this gray region means that it should be encoded over Hilbert space of B and C. But you cannot encode that individually in B and C, because you can look at this diagram here, and you can instead look at the complement of this red region, which is a white region. Then you see that the entanglement wedge of region C does not cover this gray dot. So that means that region C by itself cannot know about this gray point. Similarly, region B alone cannot know about this gray point. On the other hand, if you consider combined Hilbert space of B and C, you can know about the gray point. So this seems a bit surprising. So what's going on is a question, and that was answered this. So basically, they pointed out that the information about this gray region is encoded in the entanglement information between B and C. So if you just know about B, you cannot know about this gray, and if you know about C, you can know about this gray region. But if you combine both of these and decode the entanglement information, you can reconstruct this gray dot. So that's what they pointed out, and they also pointed out that the way it works is exactly like the way that quantum error correcting code works in quantum information theory. So error correcting code is something we use on our PC every day, the classical error correcting code. And the basic idea is that duplicate the information. So if you duplicate the information, and if you have sufficient duplication, then even if one of the bit flips, you can restore it by checking with other copies. But you cannot do that for quantum computer because there are things called quantum Xerox principle, no Xerox principle. And that means that there is no unitary process to turn state vector into tensor product of the same state vector. But you can do something similar to that, which is consider tensor product of Hilbert spaces, and consider some subspace of the Hilbert space, which has lot of entanglement information between original Hilbert spaces. So you consider, suppose you consider Hilbert space H, and you make copies of the Hilbert space. So suppose you make n copies of the Hilbert space, and consider diagonal subspace of that tensor product. So that's stating that Hilbert subspace contains entanglement information between different edges. Then if you do that, then even if information about one Hilbert subspace, one of the edge get lost, you can reconstruct it. So this is like similar kind of situation here, that information about this gray dot is encoded in this entanglement information. So this turned out to be crucial in proof that there is no global symmetry in unitary space. So let me explain why this is. So I'm going to use another fact about symmetry, which is a generalization of the Noether theorem. So Noether theorem says that if you have continuous symmetry in quantum field theory, such as Lie group symmetry, then there is always a Noether current, conserved current, and then so if you have symmetry, then there is a unitary operator that implements a symmetry on the Hilbert space. But that can be expressed as the exponential of the I times Noether charge. And the Noether charge is expressed in terms of the integral of Noether current. So that means that suppose you have a symmetry group G and you have an element, then correspondingly there is an action or unitary group action associated to the symmetry. And that can be expressed as the exponential of the corresponding Noether current integrated over the space-like section. So you have a time, and then you have a Cauchy surface, and then you integrate the Noether current over the Noether charge over Cauchy surface. So this is, of course, we teach for graduate students, right? But then supposing, so let's call this as R to meet with my notation. So I choose R to be the Cauchy surface. But suppose this Cauchy surface is divided into segments, R1, R2, R3. So then obviously the integral over R is the sum over n integral of Noether charge over these subregions. So that means that since this is exponentiated, you can write it as a product of exponential of integral of J0 over each of the regions, right? And so this is a formula I wrote over here. So namely that supposing you have a Cauchy surface R for the quantum field theory, and if quantum field theory has symmetry group, global symmetry group G, then there is a unitary operator like that. And if this Cauchy surface is a union of disjoint subregions like this, then unitary operator can be decomposed into product of unitary operator acting on each of these regions. So this just follows from the data set. Like I claim that this works not only for continuous symmetry where existence of data current guarantees it, but also for discrete symmetry. And this is actually a very interesting theorem in algebraic quantum field theory, that for any global symmetry, this is true. Yes?
Just to make sure I understand. So in the case when the region has boundaries,
yeah.
How do you define this unitary operator? Is there any
so here I'm considering the case when there is, you mean the definition of this itself?
No, just when you R is this union of disjoint the subregions, if the
subregion has to have boundaries, yes, clearly.
So what is your prescription in defining U when Ri has boundaries?
Yeah, so this is an interesting question. So U is conserved. Yes. U of GR is conserved. U of GRI are not necessarily conserved.
Yes.
So this is defined only by the action of R. It's sort of inside of this region R, right? And it's not specified how it is, what we need to do on the boundary. So one of the prescription is that whatever you do, they cancel out so that this gives you the desired unitary operator. So for this decomposition, the choice of boundary term is not too important. Yeah, so for this question, it's not very important. For example, when you have unitary continuous symmetry case, you can just define this by integral of Noether current over subregion. So in order to prove this theorem in most generality, including discrete symmetry, one has to worry about what you do on the boundary. Yeah. But if you are not interested in the most general case of this, it is sufficient to just consider continuous symmetry case for the purpose. Then it just follows from the original Noether current, Noether theorem. So let's consider this case. I just wanted to assure you that this also some version of this is also true for discrete symmetry as well as continuous symmetry. And with these two preparations, I made two preparations. One is entanglement wedge reconstruction, and the other is generalized Noether theorem. So if you know about these two, then it's sufficient to prove the following theorem: that quantum gravity in ADS has no global symmetry. Because supposing that the gravitational theory in ADS has global symmetry, not gauge symmetry, but global symmetry, that means that there must be a local operator in the bulk that transforms faithfully into another local operator. This is sort of definition of global symmetry. If you have gauge symmetry, you don't have gauge invariant local operator that transforms non-trivially under gauge symmetry, because that's sort of oxymoron. If you have gauge invariant operator, it shouldn't transform non-trivially. Right? So, but if you have global symmetry, contrary to if you have global symmetry, there ought to be local operators that transform spatially into each other. Yes?
So why do you get to talk about local operators in the first place?
Sorry?
Why do you get to talk about local operators in the first place?
Well, so to be precise, in the gravitational theory, you have to gravitationally dress local operator. But in ADS, there is a well-defined prescription of defining quasi-local operator with gravitational dressing. And so I'm assuming that if ADS gravity has global symmetry, there ought to be such a local operator that transforms faithfully into each other. Because if it doesn't if there is no such operator, then it does not make sense even to talk about symmetry. We can say, for example, the standard model of particle physics has monster symmetry. It's just that it acts trivially to all the operators in standard model, and so you can, but that's not a useful definition of symmetry. So similarly, I would like to have this global symmetry to be useful. That means that there ought to be some operators that transform non-trivial.
But just to understand, by dressing you mean that you kind of connect them by some kind of Wilson line to the boundary?
Yeah, that's right, gravitational Wilson line. So there is a well-defined prescription of how to do that. And I'm requiring that if you want to say that the gravitational theory has global symmetry, there ought to be such operator and then transform non-trivially gravitational under this global symmetry. And I say that if such operator exists, it contradicts with what I just said in the previous two transparency, this and this. And it's because supposing you have such operator, non-trivial operator in the middle of ADS, and suppose you divide the boundary of ADS into segments like this. Okay? And suppose you have a global symmetry, then that means that you have global symmetry in the conformal field theory also, and that the global symmetry acting on the conformal field theory has to have this Noether property, that it can be divided into product of operators. So that means that you can have this kind of situation. Each one of these U of G of Ri acts on this segment like R1, R2, R3, R4. And each entanglement region, a wedge of each of these regions is not covering this point X. So that means that each one of these U's commute with this operator X. So that means that all these this unitary operator would commute with X, and that's a contradiction. So therefore, there cannot be such operator. So therefore, the symmetry has to act trivially. So that's the end of the proof.
Why is Wilson line? Because Wilson line reaches the boundary.
Yeah, the Wilson line is neutral under symmetry. These Wilson lines are constructed entirely in terms of gravitational division.
This is picture dependent if you take into account 1 over n correction.
Well, this can be done order by order in perturbation, and also this operator can be black hole. So that means that it may have finite size. But then in that case, you can divide the region into smaller and smaller regions, and then you can make the commutation. You can make this commutative as much as you like. So this is essentially the proof. But there is the essence of the proof is the following: So the idea is that in order to have this kind of local excitation and in order to have that transforms non-trivially, you have to create non-trivial entanglement over here. Namely, we see that in order to create an operator over here, like this gray region, you have to make use of the non-trivial entanglement between B and C. If you just have this region C, this won't cover this gray region. If you have just B, it won't cover this region. You have to employ the entanglement between B and C. And the problem with global symmetry is that because you have this kind of product property, so therefore this unitary operator cannot create a non-trivial entanglement between regions. The symmetry operator acts pointwise on the boundary because of this nature property. So therefore, it cannot create non-trivial entanglement between different regions in the boundary space. That's why it doesn't act on this local operator. So that's sort of the idea.
It's related to what someone was asking. So does that argument says with a violation of global symmetry should be perturbative?
Yeah, so that's a very good question. So you're anticipating my slide like over here. So let me go to that question later. But before we get to that, I would like to make a few comments. The generalization of this statement. So we just proved that because symmetry generator has this property, that there cannot be global symmetry. And there is actually an analogous statement in quantum information theory called the Easton-Knill theorem, which we learned about after we wrote this paper. It's very similar to the idea that if you have quantum error correcting code, like I just mentioned, which is considered tensor products of Hilbert space and encode the information of the original Hilbert space, then this theorem says that you cannot have a unitary operator acting transversely with respect to this encoding procedure. And it doesn't work exactly in a way that I just stated. And I also want to point out that this argument also works for spontaneously broken global symmetry. If the global symmetry is spontaneously broken, then that means that there is a Goldstone field which transforms non-trivially as a shift of symmetry. So that means that if you have a shift symmetry, it must be broken in the gravitational theory. So that means that, for example, in the gravitational theory, you cannot postulate a scalar field which has exact shift symmetry. So it has to be broken somewhere. So this is an interesting thing. Another thing is that this argument also works for discrete space-time symmetry, such as parity or time reversal. So if you have a gravitational theory, you can ask whether parity is global symmetry or gauge symmetry. And that makes a difference in the way that you treat gravitational theory. So for example, when you have quantum gravity, you are supposed to sum over different topologies. But you can ask, well, should I sum over non-orientable manifold or not? Suppose you have 2D gravity, you sum over, you have torus, but should I sum Klein bottle, for example? And this actually answers that question, because if parity is gauge symmetry, then you have to sum them. If parity is global symmetry, you have a choice of summing or not summing. And so our theorem says that in the case when this theorem applies that there is no global symmetry, that means that you are forced to sum over non-orientable geometry. Okay. Now I would like to also explain that there are exceptions to this, like 2D gravity or 3D oriented pure Einstein gravity. And so this argument requires that you have ADS-CFT correspondence and you have entanglement wedge reconstruction works. For example, in 2D gravity, such as theory on the two-dimensional string worldsheet, you don't have this kind of holographic descriptions. And so therefore, this argument does not have to work. And in fact, there are 2D gravity which has global symmetry, such as, for example, if you consider heterotic string worldsheet, it has E8 cross E8 or SO32 global symmetry, which acts non-trivially on the Hilbert space of the string worldsheet theory. So therefore, this is a counterexample, but that's fine because we don't have this ADS-CFT like holography for 2D gravity. In this case, there are 2D gravity which has holographic description, but not all of them. 3D-oriented pure Einstein gravity is an interesting example because this is sort of counter-example to this claim that you have to sum over orientable manifold, because this Einstein gravity have orientation. And then I have this paper with Yifan and friends, which gives substantial evidence that such theory does not have holographic description. So this is again probably is not a counterexample. So there is even a question of whether such theory exists or not. But even if it existed, our paper seems to suggest that there is no holographic description.
In general, what you're talking about is, and this is really my make sure I'm thinking of ADS right, but the ADS really is the space-time.
Yeah, well,
So it wouldn't, so an expanding universe like a.
So it's not our universe. This is a model of quantum gravity. But it has implication to our real world, as I would try to explain later. There's also things called completeness of gauge charges. And this was most clearly stated by Joe Polchinski, I think. That is that if you have gauge symmetry in gravitational theory, then all possible charges should appear. That is consistent with the symmetry. So, namely that if you have, if gravity theory has gauge symmetry G, then dual conformal theory has global symmetry G. And then we can show that every irreducible representation of G appear in the physical spectrum. So this is called completeness theory. And this was conjectured by Joe Polchinski. And we can similarly prove that in the context of ADS shift correspondence. That was explained in your paper. So this raises a question that Sergey said that so for example, no global symmetry, if applicable to our world, would mean that the standard model has B minus L exact global symmetry, but it has to be either by broken at high energy or weakly gauged, in which case you have to have a fixed force. And if it is broken, then you can ask at what scale. So as you asked whether it's broken perturbatively or non-perturbatively. And if it is gauged, there must be some kind of force associated to it. And then how weak that force is. So this is an interesting question to ask. And also, I just said that there is a completeness of gauge charge. So that means that, for example, if the U1 U1 symmetry in the Maxwell sector is compact, then there must be some kind of magnetic monopole. And then you can ask how heavy that predicted charge should be. Okay, so our theorem does not answer these questions. But in fact, there is a stronger version of this statement called weak gravity conjecture and distance conjecture that are meant to quantify this answer to these questions. So this was suggested by Nima and the collaborator and myself and Kumran. And weak gravity conjecture says that if there is a gauge field, there must be charged particle of charge Q and mass M, such that this inequality is satisfied. I'm choosing the natural unit here. And distance conjecture, me and Kumran said that long distance excursion over moduli space generate a tau new particle with exponentially small mass, exponential in the sense of this distance that the moduli field traversed. And then if such exponentially large number of particles appears, the low energy effective theory breaks down. So this is sort of motivated by this fact that the absence of global symmetry means that shift symmetry must be broken at some level. And our distance conjecture predicts a precise way in which this breakdown occurs. So these are like more quantitative versions. And this is actually useful. So I don't have time to discuss in detail, but for example, if Kumran and I pointed out, like, when was that? Maybe 6 years ago, that if we strengthen this weak gravity, so ever since weak gravity conjecture was proposed, there is a question of whether we should have equality sign in this inequality. And so we pointed out that if this equality sign can be removed, that is that if the weak gravity conjecture can be stated with strict inequality, then you can deduce that there is a lower bound for dark energy in our universe. That is that, so we know that our universe has this dark energy. It could be cosmological constant. But interestingly, the value density of this dark energy is very similar to the expected mass of neutrino. That these two are very closely related to each other. So we pointed out that if you actually strengthen the weak gravity conjecture, then you can deduce that there is an inequality between them. And this is actually very close to the observed result. So this was pointed out by these people. And so this is very interesting that I would like to refine this further to see, because in the coming decade, both hand sides are going to be evaluated more precisely. And so it'll be interesting to find out. Okay, but that's not the talk today. So our talk, so this was just to point out that it's interesting to understand how symmetry acts in the context of ADS-CFT and how the Hilbert space is decomposed into irreducible representations. Because basically these are those questions. At least in the context of ADS-CFT correspondence, you can state these weak gravity conjecture into the question of how the Hilbert space of conformal field theory get decomposed into representation. So I'd like to present some universal result about the decomposition, and that is applicable to any unitary CFT. So this is a very simple statement, and so the statement is the following. So we can state this in the context of asymptotic density of state in high energy. So namely that I pointed out at the beginning that if you have conformal field theory, the partial function behaves like this universal form for large temperature. And then when you have symmetry, we can refine this statement. And we can refine this statement in the following way. So probability of randomly chosen state of conformal field theory with global symmetry G at high temperature T, the probability of that, if you choose random state in high temperature, probability of that state to be an irreducible unitary representation of particular, in a particular irreducible unitary representation is given by this formula. So that's our result. So if you pick, suppose you have a discrete symmetry group G, and suppose you consider high temperature state and pick some state randomly. The probability that that state in this particular representation R is proportional to the square of the dimension. So that's a statement that we proved, well, we conjectured, and I'm going to give a proof of that with Daniel Haro last year. And then, so this works out very nicely because one of the things we teach for undergraduate, for example, in the mathematical physics course is that if you have this, if you sum them, sum over all R, then it gives you 1. So it's very natural that it's a probability. Because if for finite group, you have finite number of representations, and sum of the square of the dimension of representation is equal to the number of elements of the group. So that's the basic thing you teach about finite group. If you have a compactly group, of course, there are infinitely many representations. So therefore, this formula has to be cut off in some way. So Monica Khan and Jai Hari and I derived earlier this year, last year actually. This number is wrong. I'm sorry. So this was we posted our paper actually June of this year. That this formula is cut off by the second Casimir of the representation. So there is an exponential decay by the second Casimir. But for temperature sufficiently large and for finite size group representation, this is like 1. And then it's again proportional to dimension square of the representation. So this matches up with this formula. But then as the dimension grows, it decays exponentially by the second Casimir. So this is what we derive.
So what is B?
So I'm gonna, so B is related to actually the tension of the domain wall, as I will explain. Okay, so we can similarly express this fact in terms of partition function. So I pointed out at the beginning that if you consider this partition function, it has this scaling behavior. Right? So this is followed from dimensional analysis, and this coefficient is related to central charge in 2 dimensions. If you have a global symmetry, we can consider refined version. So this is what I call symmetry-resolved partition function. That is, insert the action of the group element, and then consider trace. This is like introducing chemical potential to the partition function. So we can show that when temperature is large, it's proportional to delta function in the group in group. That is that this is 1. For finite group case, this is 1 when group element is 1, and when this is 0 when group element is not 1. For continuous group, you have to define it by with some regularization, which I will tell you. So Daniel Harrow and I showed this using holographic argument. And so I would like to explain that first because it's intuitive. And then this year with Monica and Jaiha, we come up with a more general argument that is applicable both for continuous group and finite group. So I will explain that later. So let me first explain the holographic derivation. Okay. So if you have a holographic dual, then for large temperature you have a black hole, and when you have a symmetry group G, then in the gravity side you have a gauge symmetry. Then that means that you have rational Northstone black hole charged with respect to that group. So you have such a thing over here. And then when you add the unitary group action, that means that there is some kind of group action on the boundary like that. So this is a calculation. But the thing about black hole is that if you have a Euclidean black hole, there is the boundary is contractible, boundary circle. So when you have a finite temperature calculation, you have a Euclidean space where Euclidean time direction is periodic. But the thing we learn from Gibbons-Hawking is that that circle is contractible in the black hole geometry. So that's a very important thing. So we have the following thing. So suppose you consider Wilson line in the representation R with endpoint on the boundary and I and J are indices of this representation R. So I goes from 1 to dimension of R. Okay? When the endpoints are very close to each other and the Wilson line shrink to the boundary, it should be proportional to Kronecker delta, right? Because Wilson line is starting with state I, you parallel transport and then go to the element J. So if this length of the Wilson line shrink to 0, then you should get Kronecker delta like that. But the important thing in the bulk is that this black hole, Euclidean black hole geometry has S1 is contractible. So that means that you can move this endpoint I around over here. And if you have a finite group, there is no local holonomy, so you can do that. And but the thing is that if I move this point I across this unitary operator, then you get this representation matrix D. And then it multiplies, and then you can shrink this Wilson line to a point, and then you can use Kronecker delta, and you can find this one. So by using the fact that black hole geometry is contractible, the S1 or the boundary, the thermal circle is contractible in the black hole geometry, you can derive this following identity. That is that Kronecker delta minus the representation matrix acting on this thermal partition function twisted by group element G is equal to 0 in this case. Okay. So therefore, this thermal partition function has to be a solution to this equation. So there is a unique solution to this equation that you can think for a moment, can figure out what it is. The unique solution is that it has to be a delta function in the group element. Because this means if this is proportional to the delta function where group element is enforced to be trivial, then this D becomes this Kronecker delta. So therefore this vanishes. So therefore we just derive this. So we show that we have been able to show. So Daniel and I. So this was sort of argument that Daniel and I used. That if you have holographic description for theory with finite group symmetry, then this has to be true.
But just to make sure, are you projecting onto a certain, like a chart sector of the theory?
No, this is trace is taken over all the representations. Right?
I see. Why should we expect that this should be something from 0?
Sorry?
Because of it's like if I average UG on some singlet, right?
No, this is not. This is trace is taken over entire Hilbert space, containing all the representations.
Yeah. U of G is a certain element of.
Sorry?
U of G is a given element, right?
So for given element G, U of G is a unitary operator acting on the Hilbert space. I'm inserting that in the trace. And then I derive this. Okay. This argument does not apply when G is a V group because I cannot move the Wilson line around because in general there can be a flux over here. And so this argument does not work. So, and also this works only for holographic series. So it would be nice to generalize it so that it applies to continuous group and also non-holographic CFDs. So that's what Monica and Jaiha and I did.
And Hiroshi, here you used completeness.
Sorry?
You used completeness, right?
Did I use completeness? Let me see. In this argument, you know.
Yeah.
Why?
Because, I mean, for example,
Oh yeah, I used it because in order for this to imply this,
unique solution.
you need this to be true for all the representations.
That's right.
Yes, thank you very much. Yes, but for gravitational theories that I proved this, so I'm entitled to use it. Yes, I should have said it. So Peter Weil theorem says that this. So I explained that this, if you have this, this implies this. But conversely, in order to show that this implies this, you need to state this for all the unitary representations. Thank you for pointing this out. But completeness of gauge charges guarantees this. Yeah, so this is a consequence of Peter Weil theorem. Okay, so I'd like to present an argument that works for all cases, that for non-holographic theories and also legal. And so here's an argument. So the argument makes use of the idea of low energy effective theories. So consider the, so we are considering the theory compactified on the thermal circle times some one-dimensional lower space, right? So this is kind of situation we are interested in. And in CFT, we are interested in the case when sigma is a sphere, but we can consider general situation. So so basically the idea is that to compactify this theory on the thermal circle and write the low energy effective theory in one-dimensional lower. Okay, but suppose we couple the when you twist this thermal S1, couple it to the background gauge field. The reason we do that is that because we want to mimic the effect of inserting this unitary operator. Insertion of unitary operator means that you have a holonomy around this boundary circle. And that can be done by turning on some background gauge field coupled to the. So on the CFT side, this group is a global symmetry, so there is no gauge field. But doesn't prevent me from introducing background gauge field to it. And so then we can write down low energy effective theory for the background gauge field, assuming that all the original degree freedom acquire thermal mass and decouple at high temperature, then we can write down low energy effective action for the background gauge field. And then it should have this kind of form. The leading term is proportional to the volume of the space multiplied by the temperature to the d-1 and is a function of the holonomy of the gauge group. There are subleading terms which is, for example, proportional to the square of the field strength of the gauge field, etc. But that will be subleading in temperature. Nice thing about conformal field theory is that we can count the power of temperature by dimensional analysis, and we can see that this is a leading term. So kinetic terms such as d phi square, where phi is the holonomy, or F square, which is the field strength on this sigma d-1, are suppressed by 1 over t, actually 1 over t squared. And also by diffeomorphism invariance, we can see that this potential at high temperature is independent of the geometry. So we can choose any geometry you like to calculate this V. So that's the sort of idea. So since I'm entitled to consider any geometry, so I can choose this geometry to be circle times one-dimensional lower space. So I choose this to be geometry. So then the whole space has a thermal circle times this new circle times one-dimensional, two-dimensional lower space at temperature T. And we can show that, I'm going to show that in this setup, we can relate this V of G as a tension of domain wall, implementing the twist by group element G. So let me explain. So the geometry we are considering is a thermal circle times additional circle times this sigma of d-1. So let me draw this part where you have this thermal circle times which is this black circle and additional circle which is this red circle. Okay. And I'm implementing the group action around the thermal circle. So as you go around the thermal circle, you get some action of the group, which means that this unitary group is integrated over this additional circle S1 tilde. Okay. So then, but then you can, so as usual in this kind of business, you can pretend, originally you had this as a thermal circle and you had this as an additional circle, but you can exchange their role. And you can think this red thing as thermal circle and black thing as a space-like circle. And then from that perspective, this unitary operator can act like a domain wall. So it is just as if you have a domain wall localized on this thermal circle. So then you can estimate that the temperature, this exponent should be proportional to the circumference of this new thermal circle S1 tilde times the volume of the rest of the space times the tension of the domain wall. So that means that this if this V of G is domain wall, it's very natural to expect that V of G has global minimum at G equals 1. Because if you have a domain wall which implements some non-trivial rotation, non-trivial action of the group symmetry, that would increase the energy of the ground state. And in 2D CFT, you can actually show that explicitly. And so it's natural that it has a global minimum at G equals 1. Well, for us, for my paper with Monica and Jaiha, we presented this as an assumption. So we are now actually working with Shurdeep Pal and the collaborator in San Diego to give more rigorous derivation. And so that will appear, I hope, shortly. And so assuming this, we can have the following statement, that this thermal partition function twisted by group element G is given by exponential of temperature to the D-1 times the tension of the domain wall. And since if the domain wall tension has a global minimum at G equals 1, then as temperature goes to large, it should be proportional to the delta function. It should enforce that group element has to be equal to 1. So finite group case, you can actually go to all the way to high temperature, and then you can prove that it is equal to this. Now, if you have this Kronecker delta in group finite group, which enforces G equals 1, you can expand it in this way. This is another formula we teach for undergraduate students, but let me write it because this is an important formula. So one of the things we teach undergraduate students is that if G is a finite group, and then if you choose two elements, then the Kronecker delta of the two elements is equal to 1 over the size of the group times sum over all the irreducible representation of the group, chi over R of G1 star chi over R G2. So there is this beautiful formula like that. So therefore, in particular, when one of the group element is 1, the Kronecker delta, so in particular, G and identity is equal to 1 over G times sum of a representation. If this is 1, then this becomes the dimension of the representation. Oh, and so therefore this is the dimension of R times chi R of G. So that's what I wrote over here. So you can derive this, and then therefore from that you can deduce that the density of high energy state transforming in the representation R is given by this formula. So this is what I promised at the beginning. And for compact group, this is a global minimum. We can expand around it, and then if you go to if you expand around 5, it should go like this, and then there is a quadratic part, and then this. So if asked what B is, So B is related to this quadratic part in the tension of the domain wall. And so you can derive this formula, and from that you can infer. Oh yeah, in order to go from here to here, you have to do a Fourier transformation on the group manifold. So there is this beautiful theory about the harmonic analysis of a group manifold, which we can employ. And then by doing the Fourier transformation of this over group manifold, you can convert this quadratic piece into the second Casimir. So here this is expressed in terms of group element. So there is a formula analogous to this formula for compact V group. And by using that, we arrived at this expression. Okay? So from that we can deduce that probability of finding high temperature state in particular representation R is proportional to the dimension square of the representation, just like in just a finite group case. But then there is some additional cutoff piece because you have infinite many representation. Okay. Examples. So we worked out various examples to verify that explicitly. So for example, in free field theory, we can calculate this explicitly. So for example, massless scalar, this A and B are given by Riemann zeta functions. For free spinors, these are also given by Riemann zeta function. And two-dimensional case, we can actually check that this is consistent with the Cardi formula, and this is what it should be. Holographic case is more interesting because in holographic case you consider a rational Nordstrom black hole in unit space and for non-abelian group G. And in fact, there has been long-standing question in the general relativity literature about the following fact: that in this case we are interested in a situation where you have rational Nordstrom black hole associated to non-abelian gauge group G. And in general, there are actually two types of rational Nordstrom black hole. One is that one is the following. So if you twist the Poisson function by group element in non-abelian case, you can always conjugate that so that G is diagonalized. So then you can consider this as a bunch of U1. So suppose gauge group has rank R, then you can consider U1 to the R, and you can consider U1 rational Nordstrom black hole as a sort of candidate for the bulk geometry. But in general relativity, people discovered, and in fact this was reviewed in this paper, that there are actually, so here is what I wrote. So there are two possible candidates. One is a rational Nordstrom solution with commutative gauge field with in the non-abelian theory with U1 to the rank G. And there is however also genuinely non-abelian solutions. And which one is more dominant at high temperature has been a long-standing question. And one of the contributions of my paper with Monica and Jaiha is to resolve this issue. And we have actually shown that for high temperature limit, this has the same thermodynamic behavior. And this is actually as expected because this is actually very intuitive. Because if you have a black hole in unit space, and if you raise the temperature and therefore the mass of the black hole large, the horizon grows and grows toward the boundary. But as you go toward the boundary, there is this redshift effect, and the fluctuation of field gets suppressed toward the boundary. So that means that even if you have a non-abelian gauge theory in the bulk, it gets abelianized toward the boundary because coupling constant gets suppressed toward the boundary. So the distinction between the product of rational Nordstrom solution and genuine non-abelian solution disappears as the size of the black hole becomes large. And so this is an intuitive expectation, and we have been able to actually show that to be the case. But then you can ask, well, if you consider 1 over T effect, what happens? And we were able to show by numerically calculating the free energy in both solutions that the solution with no abelian here is more stable, that it has a higher free energy. So this is so anyway. So we with this kind of result, we were able to evaluate this coefficient A and B explicitly, and so these are the formulas.
But there is a phase transition, so there is a crossing moment.
No. It's sort of it's always like so. Basically, that if you calculate free energy, then it converges for high temperature, and then one of them, the Noetherian one, is always preferred for finite temperature. Okay, so that's our result. Of course, there is a Hawking phase transition. So if you go to lower temperature, there is a region where the thermal ADS is dominant compared to the Reisner-Norton solution. So anyway, so this is our result. So this is a summary. So we have shown that for high temperature limit, the probability of randomly chosen state at high temperature to be in the representation R is given by this formula for finite group and this formula for compact group. This was originally motivated by Haro and I in the context of a holographic theory, but now we have a more general derivation of that based on low energy effective theory. So I'd like to flash some results that we are working on with David Simons-Duffin and Nathan Benjamin and Jai-Ha Lee. In the case with spins, and it's actually interesting, there are something non-trivial about it, but I just flashed it. And so that's the end of my talk, and it's 3 o'clock. Thank you.
Hirosi for the beautiful talk. Any questions? Yeah, go ahead.
Yeah.
So when you wrote down your formulas, the high temperature behavior was some power d-1.
Right, yes.
You did not take into account, is it possible that there are logarithmic corrections in temperature?
There is a logarithmic corrections for theories that are pathological. So I didn't explain this, but in fact, for example, in this case, for example, I wrote this free massless scalar for a theory where you have, so suppose you have free massless scalar. So here I'm considering complex massless scalar so that the phi transforms into e to the I cube. So we are considering this kind of thing. So you asked logarithmic correction, so I give you an example. So suppose you have a scalar theory which so this is a complex scalar. And it transforms like this. So usually I use phi for the phase. So suppose you have the U1 action which is like phase like that. And then you can consider Lagrangian density which is like del phi star del phi. So we can consider such a theory. And we calculated the corrections. We calculated the high temperature limit of the partition function. There is actually a beautiful theory about how to do this for higher dimensions. This was developed by Sir Deep Par and collaborators recently. And so we used that to calculate this. And then we got this result. But we said that this is for d greater than 4. And for d equal 2 and 3, you actually get the logarithmic term over here. So you don't get t to the d-1, but you get t to the d-1 times log of t in these two cases. And these are consequences of infrared divergence of these theories. As you know that in two-dimensional case, the massless scalar theory in flat dimension, flat R1 actually does not exist because of the Marmy-Wigner and Coleman theorems. In finite temperature case, d equals 3 is also problematic because in the high temperature limit, it essentially behaves like two-dimensional because the thermal circle direction gets compactified. So in both cases, there is actually infrared divergence, and that is reflected as the logarithm over here. In order to have logarithm, you have to have infrared divergence because log needs to have some additional dimension for the thing, right? So that calls for some infrared divergence.
The reason I asked this question was that we know that in JT gravity,
yeah,
free energy has a linear term in temperature,
okay,
and a logarithm.
Right. Probably JT gravity, because JT gravity is dual to one-dimensional thing. should probably have even bad infrared divergence. I don't know. If you don't have a spatial extent, I don't know what infrared divergence means, but presumably there is one. You can also see that for lower dimension, this is problematic because you have zeta function. So zeta function has divergence at one.
Great. Any more questions for Hirosi? If not, let's thank Hirosi.
Thank you.